Hi guys, this is our second lecture in Unit 2, and this is also the second topic that we're going to be discussing in Unit 2. So this is our topic on cell size. Alright guys, so this is or required course content. There is one learning objective, and that's for us to be able to explain the effects of surface area to volume ratio on the exchange of materials between cells, or organisms and the environment. There is a formula that we need to be able to apply when calculating the surface area to volume ratio. And based on what the surface area to volume ratio is, we should be able to use our essential knowledge to explain the effects of surface area to volume ratio. So surface area to volume ratio affects the ability of a biological system to obtain nutrients, eliminate waste, acquire or dissipate thermal heat, and otherwise exchange chemicals and energy with their environment. All right, so let's get into it. All right, so the size of a cell pretty much determines the ability of the cell to get rid of metabolic waste, and also just metabolic processes overall. Cells carry out various metabolic reactions, and the size of the cell will determine if those metabolic reactions are even possible. All right, so what are some of the things that cell size determines? Cell size determines the ability of the cell to get rid of waste, so waste material should leave cells. Also, thermal energy should dissipate from cells, so that's also leaving or exiting the cells. And what goes inside the cell? Nutrients and other useful resources and chemicals will enter the cell. So the size of the cell determines the ability of the cells to pretty much carry out these three core functions. All right, so surface area to volume ratio. So this is pretty much the focal points of this topic. The size of a cell will dictate the function of the cell. Cells need a high surface area to volume ratio in order to optimize the exchange of materials to the plasma membrane. So here's the key takeaway. A high surface area to volume ratio is good. All right, so surface area to volume ratio can be calculated depending on the shape of the cells. So remember that cells are specialized and different cells have different shapes. And there are a few formulas on the formula sheet that can be used to calculate the surface area to volume ratio. All right, so formulas for cuboidal cells. The total surface area is equal to the height times the width times the number of sides and times the number of boxes in the cell. And the total volume is the height times the width times the length and times the number of boxes of the cell. So surface area to volume ratio is the surface area divided by the volume, and whatever number is whatever value we receive from that, we can compare that to other cells, or we could just look at the value to determine if that is high enough. And remember, the key thing is high surface area to volume ratio is good. So that is ideally what cells want. Also, there is a formula for calculating a cell that is spherical. So if that's more like an oval or spherical shaped cell, it is the surface area is equal to 4 times pi times the radius square of the cell, and the volume is 4 divided by 3 pi times the radius cube of the square of the spherical. And again, the surface area, whatever that surface area is, and whatever that volume ratio is, you would divide those two. Key thing to remember, all formulas are given on your AP exam. So one of the key takeaways here is always whenever you're asked to calculate the surface area to volume ratio, is always check to see what shape the cell has. Sometimes you'll see the shape if it is a picture or a visual representation on your paper, or sometimes it is described as one of these two shapes. So always make a note of that. And I know that you guys can do the math. You can plug whatever numbers are there. You can plug them in to calculate the surface area to volume ratio. All right, so here's some quick practice. So here's an example or examples of cuboidal cells. And here we have number one. So this is cell number one, and these are cell number two. And we're trying to determine which of these, one or two, would be best at exchanging materials through the plasma membrane. So remember, the key thing is the one that has the higher surface area to volume ratio is the one that is the most effective or efficient in exchanging substances. So let's start off with one. So when calculating the surface area, remember that the surface area is, let me get my little thingy. The surface area is going to be the height of the cell times, and this is a cube, so the height of the cell is also the same as the width of the cell, times the number of sides on the cell times the number of boxes, right? And that gives us 44 units square. The volume is the height times the width times the length times the number of boxes. So we have one box here. So our volume works out to be 27 units. And in order to determine our surface area to volume ratio, we have to divide these two. So it's going to be the surface area, which is 54 units square, divided by the volume, which is 27 units cubed. And that gives us 2. So our surface area to volume ratio for question 1 is 2. All right, so remember, we're trying to determine which of these two is most efficient at exchanging materials across the cell membrane. So let's do the same thing for these cells on this side. So first, we're going to try to determine what is the surface area to volume ratio. So again, it's going to be the height, which is the height of one cell is 1. So it's going to be the height of a cell times the width of the cell, which is also going to be 1 because this is a square, so this is cuboidal, times the number of sides, so a cube has 6 sides, times the number of boxes, right? Which is 27. Now, when we plug this in, we're going to get 162 units squared. Right. And now we're going to do the volume. So volume again is going to be the height times the width times the length times the number of boxes, and that gives us 27. So to find our surface area to volume ratio, that's going to be 162 divided by 27, and that gives us 6. And your answer should be very obvious because remember, the higher surface area to volume ratio is the one that is going to be the best at exchanging materials. So option 2, which is this one, has a higher surface area to volume ratio. So that is the correct answer. Okay. Okay, so now that you know the formula for calculating the surface area to volume ratio for a spherical cell, let's try this example. So similar to our previous example with our cuboidal cell, we're going to try to determine which of these two cells is more efficient at exchanging materials across the cell membrane. So here we have cell 1 and we have cell 2. When you see questions like these, you're going to be given some values for the radius, possibly. And we know the formula. So the surface area to volume ratio is going to be 4 times pi times 5 cube. And we know that this 5 cube is the radius. So that was given in the question. If you are uncertain as to what pi is 3.14. So I'm going to try to draw it on here. 3.14. And that is pi. So that's standard. That's not on your formula sheet. That's just something you're meant to know. So that is what the value of pi. So this is pi and this is what the value of pi is. And that's a given, so that's never going to change. All right, so if we could plug this in, so if you multiply and try it for yourselves, guys, pause the video, try it for yourselves. If you could plug this in, so 4 times 3.4 times 5 cube is equal to 3.14. And our volume ratio is, so the formula is 4 divided by 3 times pi, and remember pi is 3.4, times the radius cubed. So the radius is 5, and that should be cubed. If you plug all that in, your answer should be 523.3 units cube. So we're not done, because remember we're trying to determine the surface area to volume ratio. So in determining our surface area to volume ratio, we have to now divide surface area by volume ratio. When you do that division, guys, you should get 0.6, and that's for number 1. So cell 1, the answer is 0.6. All right, let's hop over to cell 2. For cell 2 is a larger cell, evidently, and the radius for the cell is 8. Now, plugging this into our formula, for a surface area, we're going to have 4 times pi, and remember pi is 3.14, times the radius cubed, and that should give us 803.8 units. And then the volume ratio formula is going to be 4 divided by 3 times pi times the radius, but this time it should be cubed. So the radius should always be cubed for volume. And this is the value that we get, 2143.6. Now, if you divide these two, so surface area by volume ratio, your answer is 0.37. Now, the question is asking which of these are best at exchanging materials. The one that is best at exchanging materials is always going to be the one that has the higher surface area to volume ratio. So 0.6 is higher than 0.3. So the correct answer is cell 1. It's option 1. Okay, so what does this mean for cells? Cells that are small, which most cells are, so most of our cells are microscopic, they have a higher surface area to volume ratio, and therefore they're a lot more efficient at exchanging materials. So they optimize exchange of materials from the plasma membrane. When cells are larger, they have a lower surface area to volume ratio, and remember, low is not good, and therefore they're just not as efficient in exchanging materials across the cell membrane, and the cellular demand for resources will increase. Think of like if you were to run across a football field. If you are a cell particle trying to run across a large stadium size football field, it's going to take you a longer time to get across because the football field is large. Now, if this were not a stadium sized football field and this is a small football field at, say, a daycare, and you were to run across the football fields that the little toddlers run across, it's going to take you less time to get across a smaller football field, and therefore less time is wasted trying to go across, and less energy is wasted, and therefore you get across faster. So when materials are diffusing into or out of the cell, if the cell is smaller because of the surface area to volume ratio, it means that they get into or out of the cell much faster, as opposed to having a lot of in a larger cell more space to cross versus the surface area to volume ratio. So if large cells have low surface area to volume ratio, that's not good. Small cells, ideally, they're better for gaseous exchange because they have that high surface area to volume ratio. And this is it for our topic on cell size.